Anil Kumar sir, shall we start, sir?
Yeah, please.
Yeah. I will read about you, then. Yeah. Dear participants and resource person, now we have successfully completed 4 days. It is the 5th day. Now we have a resource person, a eminent person in the speech processing area, Dr. Anil Kumar Uppala, Associate Professor, IIIT, Hyderabad. Now I will give you his brief profile to you all. Anil Kumar Uppala received his BTech degree in Electronics and Communication Engineering from JNTU, Hyderabad in 2005, MTech in Electronics and Communication Engineering from NIT Kurukshetra in 2007, and PhD in Signal Processing from IIT Kharagpur in 2012. From March 2012 to June 2019, he has worked as assistant professor at IIIT Hyderabad. From July 2019 onwards, he is working as associate professor at IIIT Hyderabad. His research interests lie primarily in speech processing in mobile and practical environments. He has published 5 book chapters, 25 repeated journals, and 74 international conference papers. He is currently handling 2 sponsored projects and completed 7 funded projects. He is guiding 5 full-time PhDs. 2 of them have submitted their thesis, and 9 MS students. He successfully guided 4 PhD students and 2 MS students. He has given more than 75 invited talks in various workshops and conferences. So this is the brief profile about Dr. Anil Kumar Uppala. Thank you, sir, for inviting our request and gracing this occasion for the benefit of our ATAL FDP participants. I request you to take over the session.
Yeah, thank you, sir. Thank you, Narasimhulu sir, for inviting me here. Let me share my screen. Can you see my screen?
Yes, sir, it is coming.
Yes, sir.
Yeah. I will talk about time frequency analysis and its need in with the example of speech. Okay, if time permits, maybe example of image as well. So, first of all, can anybody tell what is this time frequency analysis means? What do you mean by this title, time frequency analysis? Yeah, there are enough participants, right? So, can anybody say what is this time frequency analysis? What do you understand by that title? What do you get by the title, time frequency analysis? No one, no? Okay, the appropriate title. Yeah, it is very difficult to teach a laptop, right? From last 3 years, my laptop might have got doctorate degree already because she is listening so many talks. So yeah, we are missing face-to-face interactions. Anyway, so time frequency analysis. So what it means is that actually the right title here is that TFA instead of TFA, the right title is joint time frequency analysis. So what it means is that we want to see both time and frequency separately. Sorry. We want to see time and frequency jointly. Okay, that is the joint time frequency analysis. Okay. So can anybody say what is the need for this joint time frequency analysis? Why we need this joint time versus frequency analysis? Or simple question, if I have a signal, I want to get a frequency information, what I will do? Anybody?
It's about number of cycles per second, sir.
If I have any signal, some signal I want to know the frequency information, what I will do in signal processing?
So how many signals per second is giving? That's the frequency.
No, let us say I have a no. I'm not defining frequency. I am telling I have a signal which has multiple frequencies. How to know what frequencies are there? What is the technique?
Sampling theorems.
No. Sampling theorem is to digitize. Sorry, analog to digital, analog to discrete actually. What we'll teach in for signals and systems and DSP? What transform will teach?
Fourier transform.
TFT, sir.
Fourier
Transform.
That is what is the purpose of Fourier transform?
Conversion from time domain to frequency domain.
Correct. So we have the already Fourier transform, right? So why we need this time frequency analysis? So if I want the frequency information, I already have. I already have Fourier transform with me, but why I need this time frequency analysis? What is the problem with Fourier transform? What is the problem with Fourier transform? What Fourier transform gives is the frequency information from the signal, but let us say so what is the principle of time Fourier transform is that we'll use what is the purpose of time frequency analysis is that Fourier transform is that the principle is that I have a signal, it has multiple frequencies. What I will do is I will use basis functions as sines and cosines, okay, because with sines and cosines harmonics we want to represent a signal, okay. Can anybody tell what is the problem with the Fourier transform? There are a couple of problems. This lecture will be interesting if you involve at least the interested candidates. If you involve and respond, whatever, you tell. If you don't know correct answer, also fine. That's how we learn. Okay. So tell, because I'm asking second year BTech stuff, right? So what I'm trying to ask is, what are the issues with the Fourier transform? Basic principle, we understand that any signal you take that can be represented with the sines and cosines, harmonics of sines and cosines, so that we know the frequencies present in that signal. So now the question is, what are the issues with the Fourier transform?
The signal should satisfy Dirichlet conditions.
Okay, my signal satisfied, no problem with that. What is the problem? Okay, so if you take Fourier transform here, right? So Fourier transform, this is a sinusoid signal, okay, which has some frequency at 5 or 25 or 50. So this has only 5 Hz, so I have got only one. My Fourier transform will be only at 5. Okay, and let us say second signal. This is the second signal which has a frequency of 25, which will get a peak at 25. Similarly, I have at 50, so I will get peak at 50. Now let us say I have a signal. This is a signal which is a combination of these three, 5, 25 and 50, right? So they are added up. Okay, so now the Fourier transform is like 5, 25 and 50. For example, imagine I have combined up to 0.45 Hz, and from 0.4 to 0.8, 25H, 0.8 to 0.1, 25H, and plot the spectrum. Similarly, I will get this only. I will get both 5H, 25 and 50. What I will miss is like, so what I will miss is that I don't know at what time that 5H is there, or at what time 25H is there, or at what time 50H is there. I don't know that, because this Fourier transform will give only frequency information present in that signal, but it won't tell you at what time what frequency is present. For example, at each point, all three are there, that is fine. But let us say for some time 5H is there, for some time 25H is there, for some time that 50H is there. If I plot the frequency Fourier transform magnitude spectrum also, I will get the peaks at 5, 25 and 50. But what I will miss is that at what time those frequencies are there, I will miss it, because this is a time domain representation. This is the time domain waveform. This is the frequency domain representation using Fourier transform. But what I want, or what we want is the joint time frequency analysis. Joint time frequency analysis, because we want to see both time and frequency at a time. Okay, for example, this is the example. You see, I have 5H here, 20H here, 50H here. They are not like this. So can anybody tell what is, are you able to see my screen?
Yes, sir. Yes, sir.
So what is the difference between, closely observe this signal, and closely observe this signal. What is the difference between those two signals?
First one is AM, second one is FM, sir.
Huh?
Amplitude modulation, frequency modulation.
No. First one is, if you observe, first one is stationary signal, because it is a combination of 5 plus 25 plus 50. Now, for every time I have these three frequencies. Or if you want confused, you go and see this signal. Is this signal stationary or non-stationary? Again, the question is, what is the stationary? What is the meaning of stationary?
Stationary signals.
What is the meaning of stationary? Stationarity?
Signal value is anticipated at any time.
Come again?
Signal value can be anticipated any time.
Okay. Yeah, actually signal, not exactly. Actually, the stationary means the signal characteristics won't change with time. Okay, the signal characteristics won't change with time. If you see this signal, at any time the signal is at 5H only. Anytime this is at 25H. Anytime this is at 50H. Or if you take this example, this is anytime is a combination of these three. Just mix of these three. So it won't change with time. If you extend 0 to 1 or 1 to 2, it's same signal. But if you see here, these are non-stationary signals, because you see here first sometime 5H is there, sometime 20. See, if I take the signal at 0.1, I have only 5H, no other frequency. If I see at 0.5, I have only 20H. If I see at 0.8, I have only 50H. Okay, I don't have any. So this is not a stationary signal. This is non-stationary signal. That means signal characteristics change with time. Did you got that point? It's a very simple point. Did you got that point? The difference between combination of 5, 25, 50 and this signal, which is sometime at 5, sometime at 20, sometime at 50. Okay. So this is called a non-stationary signal. This is called non-stationary signal. So see, observe the spectrum. Observe, let us say he has 5, 25 and 50. Similarly, we also get the peaks at 5 and 25 and 50, right? And if you go back and see, if you go back and see this signal, this also has not exactly same, but it's also giving the similar information, 5, 25 and 50. So what is missing? This signal and this signal is quite different signal. These two are not same signals, but I'm getting more or less same spectrum, and I'm not getting any additional information. Okay, but what I want is I want to see both time versus frequency simultaneously. Here I can see only time, And here see, I can see only frequency, but I want to see both x-axis time and y-axis frequency, so that I know at what time what frequency is there. That will be helpful. That is the need of this joint time frequency analysis. The main drawback of Fourier transform is applicable only for the stationary signals, and it won't be applicable for the non-stationary signals, because Fourier transform will give you the global information, or all the frequencies present in the signal, but it won't tell you at what time what frequency is there. For example, here Fourier transform is telling me that the signal has 5 and 20 and 50, that's all, but I don't know at what time 5, at what time 20, or what time 50. So which is not that useful in the practical scenario, right? So that is a problem. So we want the local information. Okay, that's where you want the time versus
Frequency,
time versus frequency information. Okay, so that's where the need of joint time frequency analysis. Now the question is what is the big deal in the joint time frequency analysis? What is can anybody tell what is the issue with the joint time frequency analysis? Is it easy, or why people have why this is a complex thing, or what it make it more challenging?
Sir, Anil sir, your mic is mute position. Kindly unmute your mic.
Yeah, it got muted. So now the question is, what is the issue with this time frequency analysis? So what is the definition of frequency? Can anybody tell what is the, now you can anybody tell what is the definition of frequency? Formula, no need to define it. What is the formula for time, frequency? Or F equal to
1 by T.
F equal to 1 by T. That means what? Frequency is
Inversely
inversely proportional to time. So that is the problem. If somebody give you one sample, I gave you sample 7, number 7. Tell me the frequency information. I just give one sample 7. Tell me the frequency information. Right, we can't get the frequency information with one sample. That means what I'm trying to say, let us say here I have some 0 to 1 signal is there. Let us say I want to know at each time, I want to know what is the frequency information. That is not possible, right? So to get the frequency information, I need to take some samples and apply Fourier transform, okay, or apply some technique to know the frequency information. Otherwise, with 1 or 2 samples, I can't get the frequency information. That means there is some kind of uncertainty. That means, let us say I'm trying to represent time versus frequency. If I see time well, I can't see frequency well. If I see frequency well, I can't see time well. Did you appreciate this point? That is a very important point to proceed further. That is the source of this course of time frequency analysis. Time frequency analysis. What is the big thing here is that there is also uncertainty principle. There is a principle of uncertainty, and even in the Fourier transform, so properties you might have except the Gaussian signal, you might know, right? Spread in the time domain is a spread. Narrow signal in the time domain is a wide signal in the frequency domain. For example, you take rectangular pulse. simple rectangular pulse will have a sinc function. Rectangular pulse is very much localized in the time domain, but the sinc function in the frequency domain is from minus infinity to infinity, vice versa. So that means there is some kind of uncertainty. Okay, so for example, there are this is a time information. This is a time frequency analysis. In that, for example, this is a time information. Okay, time versus sample. This is a frequency information. No doubt, it is frequency versus time. There is no ambiguity here. There is no double. If you compute Fourier transform or I compute, anybody compute, it will come like this only. But there is this joint time frequency analysis is not unique. I can represent this signal in time frequency analysis in many ways. This point is very important to understand. Then only we can proceed further, because there are various techniques for time frequency analysis because of uncertainty. Because there is not like I have only one perfect time versus frequency representation. It won't happen like that, because I need some samples to get the frequency. So how many samples I don't know, right? So if signal is non-stationary, if my signal is non-stationary, and if signal is changing with time, right? So this time frequency analysis has a lot of uncertainty. Time frequency analysis has uncertainty, because if I see time well, I can't see frequency well. If I see frequency well, I can't see time well. So okay, wait. So, so I will show you. For example, let me take you the example of speech. Okay. So can you see the speech signal on the screen?
Yes, sir.
Yeah, this software is called Wave Surfer, which is a free software. You can download. It will be helpful to record the speech signal or play the speech signal, etc. So this is a speech signal. By seeing the signal, can you say whether the signal is stationary or non-stationary?
Non-stationary.
Yes, the signal is non-stationary because it depends on what you speak, right? So speech is the changing one. But let me zoom it and show you. Somebody only show you this part of, oh, sorry. Okay, somebody shown you the highlighted signal. I have highlighted this one, right? So is it stationary or non-stationary? Is it stationary or non-stationary?
It looks stationary, sir.
Yeah. So it's not, speech is not completely non-stationary. This is nothing but your pitch period. This is pitch period. So this is not completely non-stationary. That's why it is called quasi-stationary. But usually other like biomedical signal or images, these are all non-stationary signals. Strictly speaking, speech is also non-stationary. Speech is also non-stationary. Okay. So if I want to know, if I want to recognize these sounds or analyze these sounds, if I apply Fourier transform on the entire signal, is of no use for me. Entire signal, if I apply Fourier transform, I will get all the frequencies. I don't know at what time what frequency is there, because this signal is different, this is different, this is different. So I can't get any information. If I apply Fourier transform on this, is useless for me. It's not useful at all. So the solution for that is one of the solution, easy solution is the short-term Fourier transform. Easy solution is the short-term Fourier transform. Short-term Fourier transform. Okay. So what they will do, instead of applying Fourier transform for the entire signal, what they will do, they will apply Fourier transform for the small windowed signal. Okay, and like that they will try to move the window. Okay, so they will apply Fourier transform for this part and plot it. Okay, that is the time and the frequency information here. From here to here, this window is for next, like that. Okay, so this is a formula for short-term Fourier transform. You already know Fourier transform, right? Fourier transform of x of t is x of t e power minus j omega t dt. In that, I am introducing something called window function. Okay, so that window will move. Okay, so what? So what is the advantage of short-term Fourier transform? For example, I have a signal here. Okay, if I apply Fourier transform for the entire signal, I will get this one. I will get this spectrum. Instead, what I am trying to do, I will write time versus frequency, and I will try to take windows. Let us say I took window here up to point. Let us say I have window of 0.2. You see this example closely on screen. Let us say I have a window of 0.2. Okay, 0 to 0.2. Then first 0.2 I will get 5. 0.2, 0.4 I will get both 5 and 20. Both 5 and 20. Next I will get for example 0.4 to 0.6. I will get only 20. 0.6 to 0.8 I will get only 50. 0.8 to 1 I may get only 50. That's fine. But this frame of 0.2 to 0.4 will give me both 5 and 20, because this signal, this window has both of them. So that is not the right spectrum, or that is not, but that at the same time that is not the wrong also, because that the window size decides everything. So we have to decide the window size. Unfortunately, in a non-stationary signal, because you see this signal and you may say that window of 0.3 is not, 2 is not good, take 0.1. That may be a good window. Okay, but you know this signal you are saying, but let us say in practical signals are non-stationary. Okay, and we don't know how should I take a window. That's why the short-term Fourier transform will give you time versus frequency information. The way I said, you apply window of 0.2, and within that window you take Fourier transform and plot it. That's how you will get the spectrum. That is called spectrogram. Actually, that is called spectrogram. But that is not much useful in many cases, because that is not very useful, because it depends on the window size. If I take window perfectly, then it is fine, but I don't know at what time window I should take. So for example, in the same speech example, it has this wavesurfer has the option to create a plane spectrogram. This is what I am talking about. So this is what spectrogram means. It's not the Fourier transform. It is the short-term Fourier transform spectrum. This is the time, same time axis versus frequency. So I'm trying to plot this one. Okay. So for example, this software is beautifully also has something called as Spectrogram Controls. So closely observe the spectrum. I have a window length. If you see, I can take a large window length. If I take large window length, what it means, I am applying Fourier transform for the entire signal. So what I will get, you can see you will get a flat spectrum. That means at each time the spectrum is same, because your window is large. That is almost like if you take window as infinite, that is a Fourier transform. In short-term Fourier transform, if you take window as infinite, that is that is the Fourier transform. So I have to choose the appropriate window, then only, and also within the window, if my signal is stationary, short-term Fourier transform works very well. Luckily in speech that happens. In speech I have shown you, right? There is some kind of stationarity. That stationarity changes, but there is some kind of stationarity. That's why short-term Fourier transform perfectly suits for speech. But it is not popular for image or any other signals, because those signals are not quasi-stationary signals. These are all perfect non-stationary signals. Speech is also non-stationary, but it is a quasi-stationary. Luckily, we have some kind of stationarity within the window. Okay, that is possible. That's why short-term Fourier transform is very applicable for the speech signals. But for other signals, short-term Fourier transform won't work. That's why if you see here, in this diagram, if you see, there are so many transforms. You can see You have a signal processing, time domain, frequency domain, fine. Time domain, time frequency domain techniques. We have STFT, fine. Next, the main thing is the wavelet transform. Similarly, we have something called Wiener-Wille distribution. We also got something called S transform. So there are a lot of transforms are there. Okay, here in joint time frequency analysis, there is nothing like it's a perfect joint time frequency representation because it's an uncertainty. You know, f equal to 1 by t, right? So I want to see both f and t properly. How it happens, right? F equal to 1 by t. That means f frequency is inversely proportional to time. So you can't there is uncertainty. You can't see all of them well, and also there is not a unique representation, right? So that's why this joint time frequency representation, lot of techniques are there. Let us say I want only frequency domain. I have Fourier transform only. That is, I have only time domain, only waveform. This is a time domain means waveform. Frequency domain means Fourier transform. But if I combine this time versus frequency, I have so much to learn. One easy technique is start from Fourier transform. That is nothing but instead of applying Fourier transform for the entire signal, try to apply the Fourier transform for the windowed signal and try to plot the spectrum that is called spectrogram, time versus frequency. And the spectrogram as I shown you here depends on your window size. Okay, spectrogram depends on window size. Okay, I can change the window and show you. Let us say if I change the window here, I am changing the window, I am narrow down. You can closely observe the spectrogram. That spectrogram the spectrogram changes. Is it changing? I have taken very narrow window. You can see the spectrum is quite different. If I take large window, spectrogram is getting uniform, kind of same thing. So your window decides the spectrogram resolution, and your window, within the window, if signal is stationary, that is a perfect. Okay, that may not happen all the time. Okay. So luckily it happens in speech, that's why it is popular. Now the question after all this discussion is, if I take a speech signal like this, answer is there already on the screen, but just I want to listen from you. So signal is already there, signal is here. So first question is, can I get different magnitude spectrums by using Fourier transform is the first question. Second question is, can I get a different spectrograms, time versus frequency using STFT? What is the answer for first question and second question? Are you people able to follow, or am I going?
Yes, sir. Yes, sir. We can get different spectrum, sir.
Spectrum, magnitude spectrums or spectrograms? First question is, I have taken a speech signal and applying a Fourier transform and plotting the magnitude spectrum. Is that magnitude spectrum unique? Is the first question. Second question is, I am taking the same speech signal, and I am taking a short-term Fourier transform. Okay, and can I get the same spectrogram all the time, or spectrogram is different? So spectrogram is different is what you are saying, madam?
Yes, sir. Magnitude spectrum depends upon the magnitude we are getting, sir. So it will be same.
Yeah. So if you take Fourier transform of any signal, that will be same. Okay, that will be that is called magnitude spectrum, and it won't change if anybody, because there is there is no variability there. But if you take the short-term Fourier transform, which results in the spectrogram, that spectrogram is not unique. As I just shown you, the spectrogram changes with your window. I am changing the window here, you are changing the spectrogram. So there is nothing like this is a perfect spectrum. No, it depends on my application. I should choose my window according to my signal. Okay, so that is why uncertainty. See, okay, if you see here, if you take a large window, I am introducing two more terms now, which you might have not heard. Is the two terms is the time resolution and frequency resolution. Time resolution and frequency resolution. Okay, so if I take a large window, what happens? I can see all the frequencies present in the signal because it's almost like a Fourier transform. I can see all the frequencies, but I can't see the time information at what time, what frequency is there, because you can see I have taken a larger window. What happened? It is showing all frequencies at all the time. It is showing all the frequency at all the time. You can observe that, right, in the spectrogram. But if I change the window, that means my window, narrow window, the advantage of narrow window is that I may not see all the frequencies present, but I can see at what time what frequency is there, at what time what frequencies. That is called time resolution. The time resolution is good if I take a narrow time, and frequency resolution won't be good. If I take vice versa, actually, if I take a larger window, frequency resolution is good. That means I can see all frequencies, but I can't see the time information. So time resolution is poor. So what is your application? Whether you want to have a frequency resolution, or time resolution, or joint resolution, depending on your choice or your need, you have to choose the windows. Okay, that is the uncertainty what we have in the time frequency analysis. But here in the time frequency analysis of the short-term Fourier transform has its own drawback, because short-term Fourier transform resolution of this time resolution and frequency resolution depends only on window size. If my window size is fixed, then my resolution is fixed. My window size is fixed, then the resolution is fixed. So that's why it is shown. It will be it will be written like this. So in the time frequency resolution of short-term Fourier transform is the time versus frequency. So I'm filling these bins. That's all. This bin depends on your window size. If your window is large, the bin will be large. Okay. So this is a kind of, that's why it is called fixed resolution. That means my window, if my window is fixed, my resolution is fixed. People thought, I don't want this fixed resolution. Can I go for a multi-resolution? So that's where this wavelet transform has come up. This wavelet is a big theory. I can't explain in a couple of hours or something. But let me tell you what is this idea. All this discussion will be just at the concept level. So if you are interested, you can go for the theory behind it. So what is this wavelets? Okay, wavelet. The meaning of wavelet is wavelet means small wave. Wavelet means small wave. So so if you have a mother wavelet function, all the basis functions of this wavelet are the dilation or scaled and translated version of the mother wavelet. Okay, so anyway, mother wavelet has to satisfy some properties, etc. But anyway, let us not directly jump into wavelets. Before jumping into wavelets, first quick, understand what are the issues with the Fourier transform. By the way, question for you: who has developed the Fourier transform? Anybody? Any guesses? Who has invented Fourier transform? Who has invented Fourier transform? Are we connected? Can you hear me?
Yes, sir. Yes, sir. Joseph
Yes, sir.
Fourier.
Yes, sir.
Who has invented Fourier transform?
Joseph Fourier.
Hmm?
Fourier himself invented.
Very good, correct answer. But unfortunately, it is wrong, wrong answer. Fourier has not invented Fourier transform. Fourier has not invented Fourier transform. It is we extended the Fourier series into Fourier transform. Fourier has proposed only Fourier series. He has not proposed Fourier transform. After that, people have extended Fourier series to Fourier transform because many of the practical signals are time limited. What is the Fourier series? Fourier series is a very mathematically proven thing that any periodic signal can be represented using, of course, they have to follow Dirichlet conditions. That is fine. Once they follow Dirichlet conditions, and what Fourier said is that whatever the periodic signal you have, you can represent that with the sines and cosines, harmonics of sines and cosine. The idea behind that is sines and cosines acts as a basis functions. So can somebody say what is this basis functions? What is meaning of basis functions? What is the meaning of basis functions? I have a two-dimensional space x and y. Can anybody say what are the basis functions for that? I have two-dimensional space, x-axis and y-axis. What are the basis functions for that? Can anybody give what are the basis functions for that?
Shifting.
Huh? No, I'm asking what are the basis functions for, let us say I have two-dimensional vector space, x-axis, y-axis, two-dimensional vector space. What are the basis functions for that? What is the meaning of basis function? Have you heard about, anybody heard about vector space, basis functions, spam, etc., span, etc., SPN, span? So just we need to, for signal processing, linear algebra is the, these are the basics are required. So here, what is meaning of this basis function is that, what Fourier has, what is a Fourier innovation is that Fourier has told that the sines and cosines acts as a harmonics of sines and cosine acts as a basis function for the periodic vector space. Periodic vector space is very huge. It is not easy to imagine that. For example, you take a two-dimensional space, x-axis and y-axis. But that is a vector space. Okay, that is a vector space. The basis functions, the simple basis functions are 0, 1 and 1, 0. They are orthogonal to each other and they can represent the basis. The beauty of basis function is that any vector in that vector space can be represented using these basis functions. Any vector in that vector space can be represented using these basis functions. For the simple two-dimensional space, for example, I have 4, 5, 6, 7 like that, two-dimensional x comma y coordinates, that vector space, any vector if you give me, I can represent using 0, 1 and 1, 0 vectors. So 0, 1 and 1, 0 acts as a basis for the two-dimensional space. Will you agree with that? Is that clear?
Yes, sir. Yes, sir.
So for two-dimensional space, okay, for two-dimensional space, 0 and 1, 0 are basis functions. Similarly, what Fourier has told is that for the periodic vector space, which is very difficult to imagine, but let us say if we have a period, if at all we have a periodic space, vector space, that can be, for that, his assumption is that sines and cosines, not one sine and one cosine, harmonics of sines and cosines, which are there from minus infinity to infinity, acts as a basis function, so that I can represent any periodic function using these basis functions. Okay, then our people that in many practical signals are not periodic. Let us assume period as infinite and extend this Fourier series into Fourier transform. If you take time period as infinite instead of finite thing infinite, then Fourier series will become Fourier transform. But Fourier transform has not developed by Fourier. Fourier has developed only Fourier series. That is what we extended for Fourier transform. The biggest drawback of Fourier transform, apart from the non-stationary signals, Fourier transform we learn in signals and DSP, but unfortunately, the basics are all are important. But unfortunately, further signal processing or for many signal analysis, this Fourier businesses don't work. Fourier is not useful actually, because Fourier series or Fourier transform will be applicable or useful only for the stationary signals, not for the non-stationary. For example, if I go for any non-stationary signals, simple Fourier transform won't work. Anyway, luckily for speech kind of signals, short-term Fourier transform works. Otherwise, Fourier transform has very limited practical applications because practical signals are non-stationary. Okay. Apart from that, that I already discussed, that in the beginning itself I discussed this issue of Fourier transform. The second issue which is highlighting is the motivation for this wavelet transform is that I have a for example I have a I have a signal like okay I have a signal like this. Okay, you can see any signal, right? 0 to 200, you can 250 it is there. 0 to 250 have a signal, but this signal is from 0 to 250. But what are the length of my basis functions in Fourier transform? What is the, can anybody tell me what is the Fourier transform formula? Integral minus infinity to infinity x of t e power minus j omega t dt. My x of t is there from 0 to 250 in this case, or 0 to 200 or 0 to some 10. But I am integrating from minus infinity to infinity because my basis functions are there from minus infinity to infinity. My sines and cosine harmonics are there from minus infinity to infinity. You understand that how, what the bad concept of Fourier transform, we are trying to we are trying to represent a small signal which is there from 0 to 250 samples, or 0 to 2 seconds, for example. 0 to 2 seconds signal I have, that 0 to 2 second signal I am trying to represent that using the basis functions which are there from minus infinity to infinity, right? For example, as if you have a two-dimensional space, I am saying simply the basis functions are 0, 1 and 1, 0. For example, somebody told minus infinity to infinity is some kind of basis function if they define for two-dimensional space, that is useless, right? So that is not the right way, right? So similarly, I have a small signal, but I am trying to represent with the basis function which are there from minus infinity to infinity. That is the drawback of Fourier transform. So then one of the solution to address this is the wavelet transform. That is the background, the motivation for the wavelet transform. If I tell now the wavelet meaning, you will understand or appreciate more well. The wavelet means small wave. The meaning of wavelet means small wave. It is not from minus infinity to infinity. It is only from limited time. Okay, small waves. The beauty of what wavelet transform says is that if you choose a mother wavelet properly, which follows these conditions, the idea here is that you can represent the signal, any signal, with this with this scaling and the translated version of this mother wavelet, combination of scaling and translated version of this wavelet. The idea is you can represent any signal using this children wavelet. Okay, that means you have mother wavelet, and if you change the T and B and A, these are the variation factors. This is a translation parameter and this is a scaling parameter. So depending on the A and B values, you will get different functions. Different functions. It is shown here. Okay. These are the different wavelets. Okay. Hope you understand what I'm trying to say. What I'm trying to say is that the basis functions for this wavelet transform is unlike your Fourier transform, where your basis functions are there from minus infinity to infinity, which your functions are there from minus infinity to infinity, right? Which is not a great idea because my signal has very low, my signal is only 0 to 2 seconds, for example. I am representing from minus infinity. Instead of that, I can use wavelet transform. This wavelet transform is, your basis functions are not there from minus infinity, they are the finite time. Okay, and you will get different wavelets using the value of A and B. Okay, and depending on A value, it represents the different frequency. Actually, this A factor, A is inversely proportional to frequency, because A is large, that means the frequency information is low. The beauty of this wavelet transform is that it will give multi-resolution. It will give you multi-resolution. Okay. So I will show you, and similarly we have something called Wiener-Wille distribution or the bilinear transformation. So let me show you some demos of different time frequency analysis techniques. Sir, what are the other topics in this course they have learned?
Sir,
What are the other topics in this course they have learned in the?
so far they have learned the image processing basics, transformations, and satellite image processing,
Okay.
and statistical methods for image processing.
Okay.
These things they have learned for these 4 days. Mostly signal
Okay,
processing
fine.
area, the
So this
depth
is-
is only.
Okay. So this is this there is a book called Cohen called Time Frequency Analysis. It's not easy to follow that book, but if you are interested, you can take that book. Soft copy is available, and this has this in the curriculum. This giant time frequency analysis is not a course in many colleges, but it is. We have in IIIT we have a course called joint time frequency analysis, and similarly we in IISc also has this course of joint time frequency analysis. So okay. It is restarting. Are you able to follow what I said so far? So this MATLAB run after running the program also I can show you. This is the waveform. Okay, so for example, can you see my screen? This one maybe a little shorter version. So I will run it and also and show you. So this is the original signal, just chip signal. That means what is the chip signal means? The frequency of the signal changes linearly with time. The frequency of the signal changes linearly with time. This is the chip signal. In that, they have taken different windows like rectangular window, Hamming window, Hanning window, and also they have taken different window sizes. They have taken initially 40 samples as a window size. Later they have taken 5 samples, 10 samples. You can see the spectrograms are different. Actually, this 40 is the right length. You can see the linear increase in the frequency, but there is a spread in the information, but there is a linearity you can observe. But example, if you take 5 only, that linearity you are not able to observe, because for this signal, what is the best spectrogram or best time versus frequency is very difficult to say. Even this one is not the best one, okay, or neither this one. It is the best among these, okay. Similarly, for the same signal, if you apply wavelet transform, right? So it will get a different, different information actually. This is usually scale time versus frequency. So it has a different resolution. It is not like your short-term Fourier transform spectrum. Your short-term Fourier transform spectrum is like this, but your wavelet spectrum will be slightly different. So if you don't understand also, it's fine. But what I'm trying to see is that this time versus frequency is lot of uncertainty is there. Depending on the technique what you use, you will get a representation. So what representation best suits for your application, accordingly you have to choose the technique. For example, I want as I told, I want speech analysis. Oh, speech is a non-stationary signal, fine, but it's a quasi-stationary signal because you have seen the stationarity. So go for short-term Fourier transform. It is very, very popular. But for example, because short-term Fourier transform beauty is that it works very well if signal is quasi-stationary. That means within the window, if signal is stationary, that is a perfect. Okay, that's why the 20 millisecond, there's a very small window they will take in speech and apply short-term Fourier transform and create spectrogram, and that is very useful. Similarly, the beauty in the image processing is that in image processing, already some of you people might have highlighted earlier speakers, in the image processing, The low frequency information is more important than high, because in the image, then more information is present in the low frequencies compared to high frequencies. Okay, that is good in this wavelets. The beauty of wavelets is that it will try to represent the low frequencies well compared to high frequencies. The low frequency information will be highlighted in the wavelet transform. Okay, that is by design, because to understand that, to appreciate that, you need to know wavelet transform, theory behind that wavelet, which I can't explain right now. But the beauty of wavelet transform is that it can highlight the low frequency information that very well suits for image processing. So that's where, before this neural network business have come, this wavelet transform, application of different wavelets on image processing and coming up with the useful features, wavelet features for image fusion or image recognition or image classification, is very popular earlier, not now, because nowadays it's all about AI and deep learning, right? So they are directly feeding the signal. So why we need signal processing? Signal processing is required because to extract the useful information from the signal, right? Either you use Fourier transform or short-term Fourier transform or wavelet, the ultimate goal is that I want to get the information from the signal, right? But this neural network is saying that don't worry, don't extract any features from your data. You give raw data to me. It is using something called convolution neural network. That convolution means itself is a filtering kind of thing. So it is extracting the useful information from the data by itself. Then all our signal processing requirement, except in some kind of medical applications or few other applications, this signal processing heavily heated because of deep learning. Because now current machine learning models are not asking for your features. I don't need wavelet feature. I don't need STFT feature. I can directly handle the speech data, or I can directly handle the image data. Okay. So that is a trend going on. But at the same time, it is better to know the signal processing approach also. So this is a wavelet transform based representation. Similarly, I have something called Convener. Yeah, this is the for this signal of chip signal, the best representation you will get for the this time versus frequency by using something called Wiener-Wille distribution. Okay, Wiener-Wille distribution, that is another time versus frequency technique. Okay, which will give you can see the which you can see very linear increase in the frequency. Okay, so but anyway, it has a problem of cross terms. You can see this information is presenting here. These are called cross terms. If you filter out these cross terms, the best time frequency representation for the chip signal will come from using pseudo Wiener distribution. Again, please catch this point. There is no perfect representation for any signal. Even for this signal, I may get other technique to get a better representation. That is leave it the matter. But what I'm trying to say, for example, I take wavelet. It is best for image. It is not best for speech. Similarly, you take short-term Fourier transform. It is best for speech. It won't be best for the image. Okay. So it is not that one technique will work for all problems. All kind of signal analysis I will use using one transform. It won't work because I have different techniques. As I said, short-term Fourier transform, wavelet transform, Hilbert-Tongue transform. Similarly, I have something called S transform or Wiener-Wille distribution. These are all ultimately will give you joint time versus frequency. They have some mathematical support, and ultimately their goal is to give time versus frequency. So some of the transform will work for some of the signals. So it is so we have to see what signal I am analyzing, what information I want. Accordingly, we have to choose the transform technique. Okay. So there is something called HHT, Hilbert-Tongue transform. What it does is that. So let us say I have a this this is a one of the latest latest transform, Hilbert-Tongue transform. Not very latest, but it is one of the compared to STFT and wavelets. This is somewhere in the late, and because STFT and wavelet has developed maybe in 80s itself. So this has developed somewhere in the late 90s. Okay, this is this Hilbert-Tongue transform also has a lot of research papers. So what it does is that, let us say I have a signal like time in temperature information, or let us say I have a weather information, okay, or the rain information. This kind of signals, if I am trying to analyze, that is the, let us say for example, weather information. which the weather in any particular place depends on so many factors. So many environmental conditions will give us the data, weather data. So if I want to use for any information from that, you want to get any information or prediction from that, we need to be careful. We can't apply on the data short-term Fourier transform or wavelets, etc. Because that is the information what we are getting because of multiple sources effect. So what they will do in this Hilbert-Young transform is that they will do something called empirical mode decomposition. What is this empirical mode decomposition? You know, these are a very mathematically very sound techniques. You may not understand this, don't worry, but let us see what is the principle behind that. This empirical mode decomposition in the layman terms, what it does, I have a weather information kind of data, I have a data signal, but this signal is very complex signal which is resulted from many sources. For example, they will apply something called empirical mode decomposition and decompose that signal into different IMFs. IMFs means intrinsic mode functions. R is nothing but I have a complex signal, I will divide that signal into multiple signals, and then each signal I will apply time frequency analysis. For each signal, I will apply time frequency analysis. That time frequency analysis, they will get something called using Hilbert transform. Hilbert transform. That's why it is called Hilbert-Young transform. So, how many of you heard about Hilbert transform? Anybody heard about Hilbert transform? Anybody heard about Hilbert transform? I think it is going above your head. Huh? At least I will be happy if you know these technical terms. Analytical signal, Hilbert transform, you know, and this joint time frequency analysis, because you know, yes, for okay. Yeah, are you able to follow? Are you able to appreciate our discussion?
Yes, sir.
Okay, so this at least if you don't know, you know, I may not be able to explain this concept of analytical and Hilbert transform, but it is a very beautiful concepts. Right? So please try to see the Wikipedia and type analytical signal, analytic signal. Okay. So what is this analytic signal? They will define the analytic signal of a signal. That means in the analytical signal there is no negative frequency component. Okay. They will take only two positive, you know, the negative component of Fourier transform also they will take it as a positive component, and negative component they will make it zero. Okay, and that they will call it as analytical signal. Okay, to calculate your analytical signal of a signal, you know, if you understand this derivation later, you will get something called S of t and S cap of t. SA of t is S of t plus J into S cap of t. This S cap of t is the Hilbert transform of S of t. S cap of t is the Hilbert transform of X of t. Why I calculate all this? You know, I am doing time frequency analysis. What is this guy is talking about analytical signal, Hilbert transform? What is all this? You know, these are required because you know, there is something called instantaneous frequency. Okay, there is something called instantaneous frequency. Okay, so you know phi, right? Phi of t, phase of a signal. You know, right? What is this phase of a signal? Phi of t, phi of t, phi of t, phi of t is nothing but tan inverse imaginary part by real part. How many of you agree? The phase of a signal is tan inverse imaginary part by real part. So that I don't know the imaginary part and real part, right? So if I have only S of t, that's why I'm creating this analytical signal is the imaginary form of a signal. SA of t is nothing but S of t plus J into S cap of t. Okay, this is the imaginary part, this is the real part. Okay, then what is this instantaneous frequency business? Instantaneous frequency is the derivative of the phase, derivative of the negative derivative of the phase. So how to get the phase? Phase I can get because I have both imaginary part and real part. That's how this instantaneous frequency has come. Instantaneous frequency has come because this analytical signal will help me to represent the signals in the magnitude form and the phase form. From the phase of the signal, I will get the derivative of the phase That is the instantaneous frequency. The instantaneous frequency means at that time what is the frequency present. So this instantaneous frequency will also give me the time versus frequency. So this instantaneous frequency also has a lot of importance in the time frequency analysis. So to appreciate the instantaneous frequency concept, you should know Hilbert transform. To know Hilbert transform, you should know what is analytical signal. Okay, this is the workflow. So in our time frequency analysis course, we'll start with the time fundamentals, frequency fundamental. That means mean time, standard deviation in time, mean frequency, standard deviation in the frequency, and then we'll say the time bandwidth product, uncertainty principle, and then this instantaneous frequency, short-term Fourier transform, wavelet transform, and Hilbert transform, like that. This course is designed like that. So there is a lot to learn. If you are interested, please follow this interesting. Many of us may not know, and even now may not know what is this analytical signal is. This analytical signal is very useful concept. Okay, analytical signal, Hilbert transform, and instantaneous frequency. Okay, so these concepts you try to please refer to this video, Wikipedia link. Okay, so this will be very useful. Okay, so in the Hilbert transform, basically why I discussed that is that in the Hilbert transform, which is actually this short-term Fourier transform and wavelet are very basic time frequency analysis techniques. They are very basic time frequency analysis techniques which are there from long. This Hilbert transform is relatively new. This, if your signal is very complex, like a weather signal or very signal which is generated from multiple components, then this Hilbert transform. For example, you are using speech, you don't need to use Hilbert transform. Just go with short-term Fourier transform. If you are using image, just go for wavelet transform. You don't need any other transform. But if you are if you are doing a weather information kind of signal or a very complex non-stationary signal, your short-term Fourier transform or this wavelet transform won't serve your purpose. For that, the popular technique is Hilbert transform. What is the principle in the Hilbert transform is that divide the complex signal into multiple signals. Okay, those are called IMFs, intrinsic mode functions. On each function, you apply the instantaneous frequency using Hilbert transform. So instantaneous frequency you will get by using d5 by dt. d5, that phase part you will get by applying the Hilbert transform. Okay, because phi is tan inverse Hilbert transform by this you can see right in the analytical signal. The phase part is because you have a signal S of t is j s of sa of t is s of t plus j into s cap of t, right? So from that you can calculate the phase part. Okay, so moving further, let me show you one small demo in the small demo in the MATLAB, whether it will work or not. Let me see. It is taking some time. I want to show some interesting demo and discuss for some time.
మీకోసం చాలా సేపటి నుంచి చూస్తున్నాము.
So in the speech signal, I have taken the speech signal. Okay. For example, okay. In the MATLAB, you have a command called sound. In that, if you use a sound command, it will play for you.
మీకోసం చాలా సేపటి నుంచి చూస్తున్నాము.
So you can listen the sentence, right? Hello. Can you listen the sentence?
మీకోసం చాలా సేపటి నుంచి చూస్తున్నాము.
Hello.
Yes, sir.
Hello.
Yes, sir. Yes, sir.
Can you listen the sentence?
Yes, sir. Listen.
మీకోసం చాలా సేపటి నుంచి చూస్తున్నాము.
It is a normal speech signal. Okay. Now, I think many of you know already this one, right? What is this one?
మీకోసం చాలా సేపటి నుంచి చూస్తున్నాము.
Okay. I will show you one more thing.
మీకోసం చాలా సేపటి నుంచి చూస్తున్నాము.
Did you observe the three things?
Yes, sir. Absolutely.
Okay, so what is happening, right? I have resampled the signal for the, if you have, no, my goal, I will explain you the example of short-term Fourier transform in the one application, that is, I have taken a speech signal. This is the speech signal I have. Okay, this is speech signal I have.
మీకోసం చాలా సేపటి నుంచి చూస్తున్నాము.
This is in the neutral emotion. I want to tell this sentence in the anger way. Okay, నేను మీకోసం చూస్తున్నాను, something like that. I want to tell in an anger way, for example. So I want to convert it into as an anger speech. Okay, so if somebody is anger, what happens? Their energy levels increase. Along with that, they will tend to speak fast. So one step I want to do is I want to make speech faster. I can do that by resampling. You can see this is the normal.
మీకోసం చాలా సేపటి నుంచి చూస్తున్నాము.
This is the faster.
మీకోసం చాలా సేపటి నుంచి చూస్తున్నాము.
You can see, right? మీకోసం చాలా సేపటి నుంచి. So this became faster, but what happened? It became like, you know already this application, right? This is a talking tom application. So it became like a talking tom application. No, I don't want to lose the speaker information. I want to know, I want to create an anger speech as if the same speaker is speaking. So same, I want to create like this, same speaker.
మీకోసం చాలా సేపటి నుంచి చూస్తున్నాము.
So I will show you the output and I will explain what. This is a kind of anger, not the perfect anger, kind of anger.
మీకోసం చాలా సేపటి నుంచి చూస్తున్నాము.
Please observe, I will play the neutral speech as well as the anger speech. You observe one thing, whether you are feeling anger or not. Second point is whether speaker is intact or not. Third point is whether you can see the fastness in the speech. This is a normal.
మీకోసం చాలా సేపటి నుంచి చూస్తున్నాము.
This is the kind of anger.
మీకోసం చాలా సేపటి నుంచి చూస్తున్నాము.
Is speaker intact? It won't become like a cat, right? Is speaker same?
Speaker same, sir.
Yeah, speaker is retained and it became kind of anger. Did you feel the anger?
Yes, sir.
మీకోసం చాలా సేపటి నుంచి చూస్తున్నాము. మీకోసం చాలా సేపటి నుంచి చూస్తున్నాము.
Right, it's a kind of became. So how it happened? It is by using short-term Fourier transform. So if you do directly in the time domain, what is happening? It's becoming a faster, but it is becoming like a cat. It's not a cat or something. It's a more childish, because usually our human being pitch is different. So children have more pitch. After that, little bit less for female, and little bit further less for male. Or you can see you can tell in the reverse order also. Compared to male, female will have more pitch. Compared to female, children will have more pitch. So I have taken a female speech, right? I have taken, this is a female speech.
మీకోసం చాలా సేపటి నుంచి చూస్తున్నాము.
So what I did, I changed the pitch. I increased the pitch. So what happened because of that? Increase the sampling rate. Because of that, what happened? My pitch increased. Pitch increased, so female become kind of more childish.
మీకోసం చాలా సేపటి నుంచి చూస్తున్నాము.
It become faster but more childish. If I do reverse, it will become slow down and become like a male, because compared to female, male pitch is low.
మీకోసం చాలా సేపటి నుంచి చూస్తున్నాము.
You can observe, right? It became like a male. Okay, it became like a male, but it became a slow speech. So I don't want that. I want to retain the pitch. I want to keep the pitch, but still I want to resample the thing. Still I want to resample. So that is done using something called phase walk order. Okay, that is called phase walk order, which depends on short-term Fourier transform. Okay, this phase walk order depends on this is a phase walk order. This phase walk order depends on STFT. What is the idea behind it is you can go through this phase. You can type the phase walk order in MATLAB. We'll get this. These are the 4 required codes. What it will does is that it. So instead of in what I'm doing in phase walk order, why it called phase walk order. I will tell you. What is this? What we are trying to do is that we are taking a Fourier transform of a signal. After that, what I'm trying to do is that I want to, let us say, I want to increase the duration. What I will do, I will repeat the frames. If I want more duration, I want to slow down the speech. Then I will repeat some frames. Or let us say I want to fast the speech. I want to make it fast. Then I will drop some frames. I will take a small by small frames and I will drop them. As I am taking a frame level, that is not at a sample level, I am taking at a frame level, which is of around 20 milliseconds, which is more than your pitch period. So what happens? Your pitch gets preserved. So your pitch won't change, but your duration of the signal will change. Okay. Even this phase walk order also can be used. I can keep the speech intact. Okay, sorry, time intact, and I can change the speaker. I will show you that demo also. For example, okay, input rate, okay, equal to input. Okay. A input हो गया, B equal to phase walk order A comma 0.6 for example, I've taken like that, and some C equal to resample B comma 06, right? 06 is 3 comma 5. Okay, let me sound the C. So you can see earlier it became faster version, right? So it became like almost like a child speaking. It was not like a faster version. You can see, for example, if you see this one, but here this is also same kind of pitch, but it is it is intact. So for example, if I do the reverse, for example, A is same input and B is for example phase walk. Okay, B is phase walk order of 1.6. C is a resample of 8 comma 5. Now let me sound C. It is like a better male voice, right? For example, if I play this one, it is a kind of dragged version, but you can see this one. This is a kind of same duration, kind of male voice. Did you appreciate it? Did you able to appreciate? Hello.
Yes, sir.
Yeah, here I am just showing the one of the example. Main application of this time frequency analysis is to extract the features and build it to a ML model. So which is not the current trend. So I am not giving those demos. So just to appreciate the a practical example of short-term Fourier transform is a walk order. You know, this I can change the pitch, or I can change by keeping the duration intact. You can see here, I can also convert into another female. You see here. Instead of 1.6, for example, let me take 1.2 and see as resample 6,5 sound.
మీకోసం చాలా సేపటి నుంచి చూస్తున్నాము.
Is it looking like another female speaker speaking?
మీకోసం చాలా సేపటి నుంచి చూస్తున్నాము.
Yes, sir.
Yeah. So I have taken the one female speaker. I can change it to the another female speaker as if like natural. Is it looking like natural without any speed up or slow down?
మీకోసం చాలా సేపటి నుంచి చూస్తున్నాము.
Isn't it?
Yes, sir.
Yeah. Like that, we can modify. You know, if you want to modify pitch, you can modify, or you want to keep the pitch same, and you want to change the duration. You want to increase or decrease, or you want to make anger speech or something like that. That also you can use this short-term Fourier transform based phase walk order. Why it is called phase walk order means you are trying to replicate the magnitude spectrum. Whether you want to you want, let's say, more duration. What you are doing, you want a more duration, you are repeating, or you are less duration, you are discarding. Accordingly, you have to change the phase and get back the signal. So that's why this is called phase walk order. Okay. So if anybody are interested in the further things, so just put a phase walk order in MATLAB. Okay, you will get it. So I know I am there in between you and your dinner. So let me summarize. What I am trying to talk today is that this many of you may be listening this for the first time. This time frequency analysis, right? This time frequency analysis is nothing but actually appropriate title for this is nothing but time versus okay. The appropriate title for this short-term Fourier this time frequency analysis is the joint time frequency analysis. Joint time frequency analysis, because I want to see both time versus frequency same time. So if I want to see only time, I can use waveform. If I want to see only frequency, I can use Fourier transform. But these two representations are not useful for the practical signals. They are non-stationary. If you tell me all the time information or all the frequency information is not useful for me, what is useful for us is that I want time versus frequency. That means at what time, what frequency is there. But at what time, what frequency perfectly we can't see, because this time and frequency are inversely proportional to each other. Okay, inversely proportional to each other. If time is good, I can't see frequency well. If frequency is good, I can't see time well. Okay. So how to put this joint time frequency representation? So there are various representations. For example, short-term Fourier transform, or that is the easy extension. That in that, what I am trying to do, instead of applying Fourier transform for the entire signal, I am applying for the windowed signal, small window. I will apply same. It works, but everything of that resultant spectrogram depends on your window size. If you take the proper window size, you will get a proper spectrum. But what is the proper window, etc., is very difficult. But luckily, in speech kind of signal, where my in the lucky part of the speech signal is that in the in speech, the window speech is not a fully non-stationary. It's a kind of quasi-stationary. If you take a small window around 20 milliseconds, I can assume my signal is stationary, and I get a I get a better spectrogram. That's why this short-term Fourier transform got very popular in speech. My problem of time frequency analysis is solved in speech case by using short-term Fourier transform. But similarly, the short-term Fourier transform may not be solution for all signals. For example, you take image kind of signal, the short-term Fourier transform not useful, and the short-term Fourier transform also has a drawbacks of fixed resolution, and this sampling function, basis functions are there from -infinity to infinity. Is not going to work for all. So wavelet transform. What is the beauty of wavelet? Wavelet means small wave. It will give multi-resolution. It will give multi-resolution, and also it will highlight the low frequencies, which is very suitable for the image processing. So image processing people have applied that. But this short-term Fourier transform and this wavelet etc. are one level of transforms. But if you want to handle a very complex signal, okay, let us say if signal is coming from only one source like image or your speech, which are coming from only one source. But let us say you are getting a signal from multiple sources. If you got a signal which is a combination of multiple sources, nowadays the popular transform is the Hilberton transform, okay, where you will decompose the signal into different signals and then apply the time frequency analysis. In that case, they are applying something called Hilbert transform, which gives the instantaneous frequency. So if anybody want to have a further understanding, please go to web and type STFT or wavelet or Hilbert transform or analytical signal. You will get very beautiful concepts of signal processing. Okay. I like to take few questions before winding up. I don't want to bore you further. I have also shown you the application of short-term Fourier transform in speech. Short-term Fourier transform is very popular in speech for speech enhancement. That means enhancing the speech, and also very popular for feature extraction, etc. But anyway, you may not appreciate those applications. That's why I have shown you the time scale modification. That means how to change the duration of the speech signal using short-term Fourier transform, which is called phase walk order. Any of you want to do a BTech project or work on it, just go for phase walk order and try to see. I have created a, let us say, anger speech. Can you create a sad speech? Like that you can you can choose some topics. Okay, so Narasimhulu garu, are you there? Is it fine? I can stop and take questions, or you are expecting something?
Yeah, no problem, sir.
Because some of these concepts, if I go further, they may not understand. That's where I don't want to scare them.
Okay, sir. No issues, no issues, sir. Now, participants, please ask any questions if you have. Please interact with the speaker, or any research topics also you can have interaction on speech processing. SAR is particularly working in the speech area.
Yeah, some of you are asking how this changes. Yeah, if you change the pitch period, that voice modulations will change. See, if I am saying I am Anil, okay, or let's say, sorry, I am from Hyderabad. If I say same sentence, if you say, the signal will be different. The signal is made different because your pitch is different, my pitch is different. Along with that, some other characteristics also different, like speaking style, etc. But major difference is the pitch. So I'm adjusting the pitch accordingly. Different voices are coming out. Okay. That's what I think Sultana madam is asking, I guess. And what are the basic parameters was taken? I didn't get you, madam. What is you are asking in the chat? Somebody is speaking, I guess. I can't hear. Actually.
Yeah, I request participants, you can unmute your mic and you can ask any kind of queries regarding the topic.
Any faculty are interested to learn more about time frequency analysis or want to do work with on this? I haven't discussed. Our lab has further techniques, our own techniques of something called single frequency filtering, which is very popular nowadays. We are getting a lot of transaction papers and very good journal papers using the time frequency analysis technique. And similarly, we have something called zero time windowing. That means that is a different version of short-term Fourier transform. We are taking a window as zero. So we have very good journal papers on that. So if anybody want to do internship or work with the projects, feel free to contact us. Okay.
Yeah, members, any queries, please? Participants?
Yes, sir.
Yeah, please. Hope there are no questions, sir. Anil, sir.
Okay, sir. Okay.
It seems there are no questions.
Yeah.
So on behalf of participants, I thank you for spending your valuable time and explaining the intricacies of time frequency analysis and its applications both in image processing and signal processing, particularly with some MATLAB codes. I am really excited and happy. I once again thank you on behalf of all the participants.